Welcome again to Engineers Newsletter Live. I'm Jeanne Harshaw from Trane's System and Application Engineering Group, and today we'll present a discussion of air-to-air energy recovery. This course is approved by the U.S. Green Building Council for 1.5 Green Building Certification Institute continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals should submit their hours to GBCI. Today's program is also registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare and Sustainable Design credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, please check your state's rules to see if credit for attending today's program can be applied to engineers' continuing education requirements. Now, there are different ways to look at energy use statistics in buildings, but most would agree, based on data from the U.S. Energy Information Administration, that residential and commercial buildings combined use approximately 30 to 40% of energy consumed in the U.S. That's why building industries spend a lot of time developing approaches to reduce overall building energy use. Energy required to condition the outdoor air can be a large percentage of that use. So that's why today we'll present strategies for air-to-air energy recovery. Trane application engineers John Murphy, Dennis Stanke, and Ronnie Moffitt will take us through a discussion of various technologies used for energy recovery and the importance of properly controlling these devices in various system types. John and Dennis will start with a detailed explanation of why designers and project teams want to use exhaust air energy recovery or may be obligated to use it to meet standards, codes, or rating systems. Then Ronnie will follow with how and how well some air-to-air energy recovery devices work. And later, John and Ronnie will discuss proper control of these devices in a system. Finally, they'll offer suggestions for cost-effective application of exhaust air energy recovery. John, will you get us started?
Air-to-air energy recovery refers to the transfer of sensible heat or sensible heat and moisture between two airstreams. The most common use is to precondition outdoor air as it enters the building for ventilation. In this case, an air-to-air heat exchanger is arranged to exchange energy between the outdoor air being brought in for ventilation and the exhaust air leaving the building. This is commonly referred to as exhaust air energy recovery. When it's hot and humid outside, energy transfers from the outdoor air to the cooler, drier exhaust air stream. When it's cold outside, the same device transfers energy from the warmer exhaust to heat the cold air entering. Now, exhaust air energy recovery devices are generally categorized as either sensible or total energy recovery. Sensible recovery devices transfer only sensible heat, while total energy recovery devices transfer not only sensible heat, but also water vapor. Now, for this broadcast, we're assuming you already have a basic understanding of the application. But to make sure we're on the same page, I'm going to breeze through this first segment to explain these two categories. And really, what better way to breeze through a segment than by standing in front of a psych chart. So this first chart depicts the operation of a sensible recovery device at cooling design conditions in Atlanta, Georgia. When it's hot outside, sensible heat is transferred from the outdoor air to the cooler exhaust air stream. This lowers the dry bulb temperature of the air entering the system, which reduces the load on the cooling equipment. At heating design conditions, this same device transfers sensible heat from the warmer exhaust air leaving the building to the cold outdoor air entering. This raises the dry bulb temperature of this entering air, reducing the load on the heating equipment. Now let's compare that with a total energy recovery device operating at the same conditions. When it's hot and humid outside, total energy recovery transfers sensible heat, cooling the entering outdoor air, but it also transfers water vapor from the humid outdoor air to the drier exhaust air stream. This has the added effect of drying the entering air. The result is that the total energy recovery device lowers the enthalpy of this entering air a lot more than sensible recovery device alone. This means that in a climate with humid outdoor conditions, Total energy recovery results in a much greater reduction in the cooling load. Now, when it's cold outside, it's also very dry. So in the winter, total energy recovery transfers sensible heat from the warm exhaust air and also transfers water vapor from the more humid exhaust air and humidifies the dry entering outdoor air. Now, depending on the application, this can improve occupant comfort by keeping indoor humidity levels a little higher during the dry winter months. One last comment on this comparison. Notice that the magnitude of energy savings at heating design conditions is greater than at cooling design. This is the case for many climate zones. It means that heating energy savings can often be greater than cooling energy savings. So it's pretty easy to understand that exhaust air energy recovery can reduce the cooling and heating energy required to condition the outdoor air being brought in for ventilation. Plus, it can allow downsizing of the cooling and heating equipment, which can help offset some of the installed cost for the energy recovery device. Of course, this device adds pressure drop to the airstream, which increases fan energy, and in some configurations may impact the size of the fan motors. So you want to make sure the cooling and heating energy savings outweighs any fan energy penalty. And finally, routing exhaust air back to the device may require more ductwork and ceiling space than a system without energy recovery.
In addition to reducing building energy use, energy recovery may be required to comply with codes, labeling programs, or rating systems. Project teams must comply with local energy codes, which means the International Energy Conservation Code in most locations. And more project teams must comply with green building codes, which means the International Green Construction Code in a growing number of locations. Project teams may also want to comply with energy labeling programs or building rating systems like LEED. These programs and systems also include energy recovery requirements, but we're not covering them today. Most local energy codes simply adopt the IECC model code because the Department of Energy has mandated its adoption in all states with energy codes, and it doesn't allow any cherry picking of these requirements. Therefore, building projects in more than 40 states must comply with the IECC. Here's an illustration showing the relationship between Standard 90.1, the IECC, and local energy codes. The IECC offers two project compliance paths. The less frequently followed ICC path includes requirements from a variety of sources and experts, but most projects use the 90.1 path, meeting all applicable requirements in the ASHRAE standard for energy. Even in states and jurisdictions that don't require it, many designers choose to follow 90.1 to ensure that LEED projects can be certified and earn energy points. For anybody who is unfamiliar with 90.1, it's the energy standard for buildings. It's a mandatory language standard with requirements intended to reduce energy use in buildings. It covers building envelope, HVAC, surface water heating, and lighting. Exhaust air energy recovery is one of many HVAC-related requirements in 90.1. Energy recovery has been in the standard for a long time. It was required in the 1999, 2001, 2004, and 2007 versions, and since codes lag behind standards, a lot of buildings must comply with an older version to meet the existing energy code. Your handout includes the exact wording from those versions, but these three bullets summarize the requirements. First, any fan system with design supply airflow of 5,000 CFM or more and with at least 70% outdoor airflow must include exhaust air energy recovery without regard to climate. Second, where required, the energy recovery system must be at least 50% effective based on the ratio of the change in outdoor air enthalpy to the difference between outdoor and return air enthalpy at design airflow rates. Finally, to avoid unnecessary heat recovery and increased energy use during economizer operation, the fan system must include bypass or other means to control recovery capacity. It's too bad that the standard uses the phrase energy recovery effectiveness in this requirement. Effectiveness usually refers to how well a device transfers energy rather than how much energy it can theoretically transfer. This design effectiveness won't necessarily match up with the actual energy transferred by the energy recovery device. It's really a measure of the maximum energy recovery capacity. So we'll refer to it today as ventilation load reduction ratio rather than effectiveness. John will be discussing this in more depth in a minute. Before too long, local codes will catch up and designers will need to comply with Standard 90.1 2010 requirements to meet the 2012 version of the IECC. Summarizing, the first provision in the 2010 requirements determine where energy recovery must be used. It has changed significantly compared to the 90.1 2007 version. Before, only systems with 5,000 CFM or more and outdoor air intake of 70% or more needed energy recovery. But for 2010, energy recovery depends not only on supply and outdoor airflow, but also on climate. Many more systems need energy recovery to meet 2010 requirements. The next two requirements don't change. Every energy recovery system must provide at least 50% ventilation load reduction and must prevent energy recovery during economizer operation. 90.1 now includes a table similar to this one. It shows how exhaust air energy requirements relate to system supply and outdoor airflow as well as climate. It's much more stringent than the 2007 version. For example, consider a 4,000 CFM system with 55% outdoor air. If located in Miami, Climate Zone 1A, or in northern Minnesota, Climate Zone 7, this system would not need energy recovery to meet 2007 requirements. But the same system must include energy recovery in both climates to meet the 2010 version. As you can see, more systems need exhaust air energy recovery to meet the 90.1 2010 requirements than the 90.1 2007 requirements. Looking ahead to 2013 version, this table will change again. In any given climate zone, the general trend for 90.1 has been to require exhaust air energy recovery for smaller and smaller systems with lower and lower minimum outdoor air percentages. Of course, many requirements in the standard have exceptions. Your handout lists them for all section 6561. Most are easily understood, but some need a little more emphasis. Exception A, for instance, says that laboratory systems don't need energy recovery if they comply with section 6572 requirements. These requirements reduce energy use by varying exhaust airflow rate rather than by recovering energy. Exception E says that energy recovery isn't needed if more than 60% of outdoor air heating energy is provided by site-recovered or site-solar heat. This encourages the use of solar heat to reduce energy use. Exception G says, essentially, that energy recovery for cooling isn't required for systems in marine, cool, dry, or cold climates because they spend a lot of time in economizer cooling. But the exception doesn't apply for heating. So many systems must still include heating energy recovery in these climates. And exception I says that energy recovery isn't needed if heat is transferred from upstream to downstream of a dehumidifying coil. In some systems and some climates, this saves new energy reheat. But be careful. If a system doesn't need to deliver neutral temperature air, or if it doesn't need reheat during most seasons, exhaust air energy recovery might still be valuable, even if not required. One of these If one of these exceptions applies, the project is not required to include energy recovery, but this doesn't prohibit you from using it. For instance, maybe you should use energy recovery in a system with heat transfer in series with a dehumidification coil, even though it's not required. You need to do an annual energy performance analysis to determine the right answer for your system in your climate. Incidentally, we've been talking a lot about climate zones. You should know that climate zones are changing. Standard 169 will soon be redefining the climate for some geographical locations. No need to go into detail here, but it's safe to say that warmer climate zones are creeping to the north in a lot of areas, so it's likely that exhaust air energy recovery requirements will be changing in some locations in the future. Wisconsin, for example, is currently about 70% Zone 6 and 30% Zone 7. But as this map shows, when Standard 169 is published, about 60% of the state becomes Zone 5, about 35% remains Zone 6, and only one northern county will still be Zone 7. That's quite a shift, and 90.1 is sure to include these new climate zones in some future version. Let's turn now to green building codes. A small but growing number of jurisdictions have such codes. Many of them are based on the International Green Construction Code, or the IGCC, from the International Code Council. Here's an illustration showing the relationship between 90.1, 189.1, the IGCC, and local green building codes. Like the IECC for energy, the IGCC offers two project compliance paths. Many jurisdictions are in the process of adopting high-performance green building codes as we speak, so it's too early to say for sure, but I think that many building projects will choose the 189 path, which automatically includes all of the energy requirements of 90.1, along with some important additions. Designers seem most likely to choose the 189 path, since they're already familiar with the requirements of 90.1 and LEED. Architects, on the other hand, may lean toward the ICC path because it seems to offer more architectural design flexibility. A project can comply using either path, so be prepared to pursue the best path for your project. Similar to 90.1, 189 is written in mandatory language for easy code adoption. Its requirements allow projects to go beyond minimum safety and energy codes to produce building projects with lower environmental impact than traditional buildings. It reduces energy use more than the minimum requirements of Standard 90.1 2010, so let's look specifically at its energy recovery requirements. Section 7436 includes these three basic requirements. Like 90.1, 189 requires energy recovery based on climate, outdoor airflow requirements, and system size. But it requires energy recovery in systems with as little as 10% outdoor airflow, while 90.1 only covers systems down to 30% outdoor airflow. This means that 189 applies to more systems. Second, 189 increases the minimum ventilation load reduction from 50% to 60%. Again, it is more stringent. It requires increased energy recovery capacity. And finally, it requires the same bypass or control requirements as 90.1 to permit proper operation during economizer mode. Of course, even though they're not listed, all exceptions in 90.1 still apply to the energy recovery requirements in 189.1. As Table 7436 shows, 189 requires energy recovery in all systems and climates included in 90.1, plus many more systems with lower outdoor airflows. For example, consider a 5,000 CFM system with 20% outdoor air. 90.1 would not require energy recovery for this system, but 189 requires it in cold climates, zones 7 and 8. And for a system with 13,000 CFM, again, 90.1 would not require energy recovery, but 189 does, not only in the cold climates, but also in moist climate zones 1 through 6, basically everything east of the Rockies. So some of you may be wondering how the upcoming 2013 version of 90.1 will compare with 189. But that's a ways off, so we're not discussing it today. But John will give us a more detailed look at present requirements.
In Dennis's review of code requirements, he mentioned the term effectiveness. Now, ASHRAE Standards 84 defines the method of testing the performance of an air-to-air heat exchanger. And AHRI Standard 1060 defines the conditions and procedures for rating and certifying their performance. These standards introduce the term effectiveness, which describes how well these types of devices transfer energy. Effectiveness is defined as the actual energy transfer divided by the maximum possible energy transfer between the two air streams. Effectiveness is determined in the laboratory by measuring entering and leaving conditions and solving these equations for either sensible, latent, or total effectiveness. Now, looking at just sensible effectiveness, the numerator is the actual sensible energy transferred. That is, the mass flow rate of air passing through the supply side of the device times the change in dry bulb temperature from entering to leaving. The denominator is the maximum possible energy transfer. Now note that if the outdoor and exhaust airflow rates are not equal, this maximum possible energy transfer is limited by the smaller of these two airflows. Now the equations for calculating latent and total effectiveness are similar, but they use humidity ratios or enthalpies rather than dry bulb temperatures. So let's look at an example, starting with equal airflows through each side of the device. At this condition, this example total energy recovery device lowers the dry bulb temperature and humidity ratio of the outdoor airstream, reducing the enthalpy from 38.4 to 33.6 BTUs per pound. This equates to 216 MBH of energy transferred from the outdoor air to the exhaust airstream. So to calculate total effectiveness, we divide this supply side enthalpy reduction by the difference in the entering outdoor enthalpy and the entering exhaust air enthalpy, 38.4 minus 29.2. The result is, at these balanced airflows, the total effectiveness of this device is 52%. Now let's look at this same device with unequal airflows. In this case, 10,000 CFM of outdoor air still passes through the supply side, but only 7,500 CFM is passing through the exhaust side of the device. With less cool exhaust air to transfer energy to, the outdoor air is not cooled or dehumidified as much, and the enthalpy is reduced to only 34 BTUs per pound. This equates to 200 MBH of energy transferred compared to 216 with equal airflows. Now, when we calculate the effectiveness, the numerator is smaller because less energy is transferred. But the denominator is also smaller because we use the smaller of the two airflows. The result is, at these unequal airflows, the total effectiveness of this device is calculated to be 64%. So the effectiveness is higher even though the actual energy saved is less. Obviously this is confusing. Most people would assume that higher effectiveness means more energy savings, but that depends on if airflows are equal or not. Now, I don't use a lot of analogies, but let me try one on you. Here's a sponge next to a large bucket of water, and here's the exact same sponge next to a small puddle of water. Think of this sponge as the energy recovery device, and the water as the energy this device transfers. So when I put this sponge in the small puddle down here, it absorbs all the water. So it's 100% effective at absorbing the available energy. when I put this same exact sponge in the bucket, it absorbs a lot more water, to the point that the sponge is saturated. But it's less than 100% effective at absorbing all the available energy, since there's still water left in the bucket. With the bucket, there's a lot more water or energy available to be absorbed. The sponge absorbs a lot more water than from the puddle, but the effectiveness is lower since it was not able to absorb all of the water available. In the puddle, the sponge absorbed less water than if dipped in the bucket, but it was 100% effective since it was able to absorb all of the water available. Like this analogy, with less exhaust airflow, the heat exchanger is actually more effective at transferring the available energy. But with less exhaust airflow, there's not as much energy available to be transferred, so less energy is saved. Remember, the term effectiveness is defined as the actual energy transfer divided by the maximum possible energy transfer between the two airstreams. So it's really meant to compare how good various heat exchangers perform under the same set of conditions, not to compare the performance of a device as it operates under different conditions. So now that you're aware of that potential source of confusion, let's throw another one at you. And really, this is the one you need to care about. Remember Dennis's discussion of ASHRAE 90.1's requirement for exhaust air energy recovery. If it's required for your climate zone and system size, then the prescriptive requirement states that 50% effectiveness must be achieved. But hold on, right in that section of the standard, 90.1 defines effectiveness as the change in enthalpy of the outdoor air equal to 50% of the difference between the enthalpies of the outdoor air and return air. So at cooling design conditions, if the outdoor enthalpy is 38.4 and the return air enthalpy is 29.2, the energy recovery device must lower the enthalpy of the outdoor air to 33.8 BTUs per pound or less in order to comply with the standard. 33.8 is 50% of the difference between these two enthalpies. The confusion here is that how standard 90.1 defines effectiveness in this paragraph is different than the definition I just showed you. In 90.1, there's no mention of mass flow rates. So let's go back to our example to see why this matters. Here's our device operating with equal airflows through both sides. At these conditions, the device lowers the enthalpy of the outdoor airstream to 33.6 BTUs per pound. This is lower than the required threshold of 33.8, so it complies with standard 90.1. But now look what happens with unequal airflows. As we saw earlier, with less cool exhaust to transfer energy to, the enthalpy of the outdoor airstream is lowered to only 34 BTUs per pound. This enthalpy reduction is not large enough to comply with standard 90.1, since this leaving air enthalpy is higher than the threshold of 33.8. So the ventilation load reduction is less than 50%. But the calculated effectiveness, using the definition from the rating standard, is 64%. So really this rated effectiveness is pretty irrelevant in terms of determining if the system complies with standard 90.1. As I explained, this term depicts how well the device exchanges energy, not how much energy is saved. One way to think about it is this. This example energy recovery device can comply with 90.1 as long as the system is designed to give it enough exhaust airflow. For this example, that would mean require about 8,200 or 82% exhaust flow. But if the system isn't designed to bring back enough exhaust air, even the most effective devices won't meet the requirements of standard 90.1. Now, in my opinion, the best way to avoid this confusion would be for standard 90.1 to change its wording and avoid using the term effectiveness. In the meantime, be careful not to confuse the ventilation load reduction required by 90.1 with rated effectiveness, which is certified performance by AHRI standard 1060. An air-to-air heat exchanger with unequal airflows requires more surface area to meet the 90.1 requirement. To minimize the size and cost of the heat exchanger, try to bring back as much exhaust air as possible. Near the end of the program, We'll talk about one way to do that.
There are various ways to recover energy from the exhaust air to pre-treat the incoming outdoor air. I will briefly review each energy recovery technology and how well each will recover energy to cool the air in the cooling season and heat the air during heating. Then I'll go over the energy cost of each. Just as heating with a boiler or cooling with a chiller, there will be an energy cost for each technology to pre-treat the outdoor air. Then with these known, the efficiency of pre-treating the air can be compared as well as a comparative look at the cost to implement. The most flexible way to recover energy from the exhaust air is with a coil loop. At minimum, 2 hydronic coils are used. A coil in the exhaust air stream recovers sensible heat from the exhaust air to a glycol solution. This fluid is pumped over to another coil in the outdoor air stream, where the outdoor air is cooled in the summer and heated in the winter by this fluid. Temperature control is accomplished by a 3-way mixing valve. The primary advantage of this technology is exhaust outlets and ventilation intakes do not need to be near each other in the building. This is especially important for applications where no cross-contamination is allowed, such as a hospital or laboratory that have harmful contaminants in the exhaust. Since this system exchanges only sensible heat, the greatest benefit is in heating-dominated climates. However, the larger the airflow and more hours of operation, the more beneficial this technology is. And this is often the case where cross-contamination is a concern. How effective this system will be at recovering energy will depend on the depth of the coil, the spacing of the fins, and the face velocity. Each technology discussed today will have similar options that will affect performance. As for a coil loop, a typical air handler face velocity at 500 feet per minute, 35 to 55% sensible effectiveness is achievable. Each energy recovery technology will have a cost at which this energy is recovered. It isn't free. For a coil loop, it will be pump energy, as well as fan energy from the component air pressure loss. At 500 feet per minute air handler velocity, the pressure loss will be 0.3 to 0.8 inches. It will vary greatly depending on how deep the coil is, which in turn dictates how much energy is recovered. So deeper the coil, the more energy saved, but more energy used. After each technology is discussed, we'll look at these trade-offs. Note that coil loops are flexible, however the coils are not mounted directly in the ductwork, where air velocity could be 4 times higher than shown. The coil needs to be mounted with drain pans as condensate is possible, access for cleaning, and a pre-filter is required to keep clean. This air handler may or may not have a fan, as it may be ducted up to a rooftop unit or some other equipment that includes a fan sized to handle this extra pressure loss.
Coil loops only transfer sensible heat, so they can't transfer a lot of energy. But they don't allow leakage between airstreams because the intake and exhaust can be separated. With low ventilation load reduction values, they don't usually meet 90.1 or 189 requirements for at least 50% reduction, but they can still be useful if one of many energy recovery exceptions applies. Exception C, for example, says that systems exhausting toxic contaminants don't need energy recovery because contaminants might be transferred. But since coils in separate ducts prevent airstream leakage, coil loops could be applied successfully in these systems to provide energy savings, especially in cold climates. Exception H says that for systems where the largest exhaust outlet is less than 75% of design airflow, energy recovery isn't required because energy potential from that single airstream is low. But coil loops with multiple coils can be used to recover energy regardless of the inlet or outlet size or location. If a system must include energy recovery, coil loops probably can't transfer enough energy to meet code. But if any exceptions apply, they can still be used as an energy recovery choice to consider.
A heat pipe will operate similar to a coil loop. It will not be as flexible as the airstreams need to be side by side. As with coil loops, the air velocity applied will be in the lower range of a typical air handler, 400 to 500 feet per minute. A unit with side-by-side airflows will be required and thus a large footprint. Leakage is limited, but each tube of the coil is continuous from one airstream to the next, making it difficult to completely seal between the airstreams. There is no pump utilized. Each one of these tubes will have a refrigerant inside under pressure. Exposing warm air to one side and a cool air on the other will induce convection, moving the refrigerant and the heat from one side to the other. Control is best accomplished by bypass dampers, though some have used a tilt control that tilts the coil, slowing the movement of refrigerant from one side to the other. Heat pipe performance is similar to coil loops, with slightly lower performance at higher face velocities. At 500 feet per minute air handler face velocity, 40 to 50% sensible effectiveness is achievable. Since there are no pumps, the only energy cost for the energy recovered will be the added energy from the pressure loss. Pressure drop will be similar to slightly higher than a coil loop.
Like coil loops, heat pipes only transfer sensible heat, and since intake and exhaust ducts must be adjacent, leakage between airstreams is possible. Where 90.1 requires energy recovery in a system, heat pipes usually can't transfer enough heat to meet the 50% ventilation load reduction requirement for most climates. But for systems where energy recovery isn't required, heat pipes can still provide some reduction in sensible ventilation load. Exception B, for example, says spaces that are not cooled and are heated to less than 60 degrees, like warehouses, don't need energy recovery. But heat pipes might provide a cost-effective approach to reduce heating load in some of these spaces, especially in cold locations. In cases where energy recovery is required by 90.1 or 189.1, heat pipes usually can't be used, but they might still provide a reasonable energy recovery option in some applications addressed by the exceptions.
Fixed plate heat exchangers, also called air-to-air heat exchangers, are cross-flow heat exchangers. Outdoor air and exhaust air flow in an X pattern with respect to each other. The exchanger consists of aluminum plates that are stamped into a dimpled or channeled shape. The plates are stacked on each other with alternating edges crimped and sealed to prevent cross leakage. These can handle high pressure differentials, some up to 10 inches between the exhaust and outdoor air side. They also can handle higher temperatures and may have an option to be coated for corrosion protection for uses in applications such as a swimming pool. Here are some example unit configurations to help show the cross-flow pattern of air. The cross-flow pattern allows for flexibility in fan placement and inlet and outlet locations. A stacked configuration with top and bottom airflows is required, but fans could be at the bottom level as shown. Because the plates are designed to handle higher pressures, the fans could be blow-through, draw-through, or draw-through, blow-through. This, combined with the fact air can come in the top or bottom, makes for a large number of configurations possible. The number of possibilities far outnumber what is shown here. Here we show a 20,000 CFM exchanger with the air handler casing panels removed to help see how these fit into a system. Air is cross-flow. For control, a face and bypass damper is located on the exhaust air side of the exchanger. It would work on either path, but exhaust air side placement prevents cold air from being bypassed. Often, air is bypassed when outdoor air is close to or below freezing to prevent overheating of the air. What also is shown are drain pans. These will be needed to collect condensate. Condensate is much more likely to occur with a plate exchanger versus a coil loop or heat pipe, not just because of higher effectiveness, but because of the uneven temperatures leaving the exchanger. During the winter time, the leaving exhaust air temperature will be close to the outdoor air temperature at the corner of the exchanger where these two airstreams cross. This condensate is good. It will increase the sensible heat gain to the outdoor airstream during heating, but one has to be careful not to put the cold corner at the bottom to prevent condensate flowing into the corner and freezing. When looking at performance for these technologies, a common benchmark for sizing is needed so coil loops, heat pipes, plates, and wheels can be compared. A way to do this is to look at the air handler face velocity when comparing performance. A plate exchanger is set in an angle, so its face velocity will actually be lower than the air handler velocity. For instance, a 500 feet per minute air handler will on average have an exchanger face velocity of 350 to 400 feet per minute. For a 10,000 CFM example, the exchanger will have a 60 to 70% sensible effectiveness. What affects this most is not just the size, but the spacing of the plates. Most exchangers come with minimum of 3 plate spacing options. The face velocity has minimal impact. An air handler at 600 feet per minute will only have a few points lower effectiveness than an air handler at 400 feet per minute. Face velocity will have a great impact on the pressure drop for the exchanger. For the previous example, dropping the air handler velocity down from 600 to 400 feet per minute will cut the pressure drop in half. Similar energy recovery results, but much less energy input required to achieve it. The typical fixed plate heat exchanger pressure drop will range from 1/3 to 1 inch, a large range versus some of the other technologies we have and will discuss.
Like heat pipes, fixed plate heat exchangers transfer sensible heat, allow some leakage, and airstreams must be adjacent. Ventilation load reduction can range from about 20 to 30% in moist climates and from 55 to 70% in dry climates. So these heat exchangers could not comply with 90.1 or 189 in moist climates, but they can usually comply in dry and cold climates. And as with other technologies, designers may choose fixed plate heat exchangers to provide heat recovery in those system applications where one or more exceptions apply. For instance, exception J says that energy recovery isn't required in spaces operated for less than 20 hours per week at design outdoor airflow. So for a church in a cold climate, for instance, a designer might choose to use a fixed plate heat exchanger to save some heating energy. In moist locations, fixed plate heat exchangers don't meet 90.1 or 189.1 requirements, but in dry and cold locations, they can exceed the 50% ventilation load reduction required by 90.1, and in some cases, the 60% reduction required by 189.
Instead of aluminum plates, a membrane material can be used to exchange heat and water vapor. Like the aluminum plates, the air flows are cross-flow, but instead of just sensible heat being exchanged, water vapor is transferred between the air streams through the membrane. These exchangers are limited in size by the membrane material. Most cores are sized for use in the 400 to 750 CFM flow range. Using these at typical commercial applications will require banks of exchangers to be assembled with the use of transitions and block-offs to get the cross-flow air through all the exchangers while still isolating the exhaust and outdoor air streams. This results in some cases higher pressure losses from the transitions than the exchangers themselves. Another limitation for the membrane material is the lower allowed pressure differential. Unlike the aluminum plates, one has to be careful on fan arrangements, as most exchangers are limited to less than 2 inches of pressure differential. The membrane exchangers' nominal face velocities are in the 200 to 300 feet per minute range. Once the transitions and block-offs required to mount an air handler are applied, a 250 to 350 feet per minute face velocity is seen at the air handler. Sensible effectiveness at this lower face velocity is in the 62 to 70% range, with the latent effectiveness varying per manufacturer in the 45 to 54% range. The pressure drop across a 500 CFM single exchanger is less than 1 inch per airstream, but adding transition losses, a 10,000 CFM unit is in the 1.5 to 3 inch range per airstream at 300 feet per minute air handler air velocity.
Fixed membrane heat exchangers transfer both sensible and latent heat, and they have low leakage, but the airstreams must be adjacent. Ventilation load reduction can range from about 35 to over 60% in moist climates and from 55 to 70% in dry climates. So these heat recovery devices may comply with 90.1 in many locations and with 189.1 in some locations, but they are often limited in airflow capacity since each core only handles about 500 CFM. Fixed membrane heat exchangers can probably meet most energy codes in most climates, but only when used in smaller or separate units.
The next technology to consider are energy recovery wheels. These consist of a wheel rotating at 20 to 60 RPM between the exhaust and outdoor airstream. In or on this rotor is a desiccant, an absorbent designed to selectively attract water vapor. The commonly used absorbents are silica gel, molecular sieve, and a polymer. As these two airstreams pass through the exchanger, the wheel will try to equalize temperature and vapor pressures of the two airstreams. As with the plate exchanger, capacity can be readily controlled by bypassing exhaust air. A drawback is cross-leakage. We'll cover that later. Some of the advantage of the wheels are if they are rotated, they are somewhat self-cleaning and will be less subjected to clogging. Another is because of the desiccant transferring moisture as well as heat, these are less susceptible to condensate or frost in the winter. The primary difference between the wheels used today is the media type. Aluminum media consists of corrugated sheets of aluminum that have desiccant glued to its surface. These are rolled into a wheel shape and spokes hold it together from a central hub. Synthetic fiber wheels look and are made similar as aluminum. However, they do not have desiccant glued or coated onto the surface. The media itself is a corrugated material that is made up of desiccant and some binders. This has an advantage that more desiccant can be applied and is less subjected to corrosion. Polymer wheels have the desiccant bonded to the surface of the polymer strips without the use of binders and glue. The primary advantage to polymer wheel is their weight. They weigh much less than others. This allows for permanently lubricated bearings and smaller motors. This also allows for removable segments for ease of maintenance. Instead of continuously wound corrugated material, these strips are affixed into removable segments in the wheel. Once the rotation speed is optimized based on depth, spacing, and desiccant utilized, there is not a huge difference between the type of wheel media or desiccant with respect on how much energy is recovered, though overall performance may vary from manufacturer to manufacturer. Shown on the graph is public data from the AHRI 1060 certification directory for air-to-air energy recovery wheels. Most energy wheels will have a 2 to 8% point difference between the latent and sensible recovery, with some of the aluminum wheels having a larger spread. The most important thing to conclude from this is when specifying energy recovery wheels with latent and sensible recovery, this requires two numbers, latent and sensible effectiveness. Total effectiveness is a calculated value that will fall between these two numbers and will vary based on an outdoor condition. Certification data was taken at various air velocities. As with the plate exchangers, looking at the air handler face velocity will be more applicable than the rotor face velocity, as I don't believe there are many who manufacture around air handlers. Energy wheels are typically used at face velocities greater than 700 feet per minute, which corresponds to air handler face velocity in the 500 feet per minute range. As typically applied, wheels have a 60 to 76% sensible effectiveness and 55 to 70% latent effectiveness. To get higher effectiveness, one can upsize the equipment, but the slope of these lines are not too steep. Upsizing your air handler from 500 feet per minute to 300 feet per minute, a 66% increase in equipment size, only results in about a 10% increase in performance. What about the energy cost of this energy recovery? The first cost of recovery is the pressure drop. In a 500 feet per minute air handler, a typical wheel will have a 1-inch pressure drop. Airflow through an energy wheel is laminar, so the impact oversizing the wheel will not be as great as for a coil or device with turbulent flow. The results are linear versus parabolic. Upsizing the unit 50% will have approximate 50% drop off in pressure drop. An additional cost of recovering energy with an energy wheel is the motor required to rotate it. Energy wheels rotate from anywhere between 20 to 60 RPM. This requires either a gear motor or a specialty motor. The motor utilized is going to rotate less than off-the-shelf 1800 or 1200 RPM motor. Motor size varies depending on wheel type and size. Because of the lighter weight of the polymer media wheels, these have the smallest motors, most sizes requiring only 1/6 horsepower. The synthetic fiber wheels will vary more on size, 1/4 horsepower to 2 horsepower for the largest. Previous generations of aluminum wheels commonly used 5 horsepower on the wheels. The latest generation of wheels has switched to gear motors and lowered this down to fractional motors in many cases also. One of the largest and varying costs of recovering energy with a wheel is the cross-leakage of air from one side to the other. This cross-leakage results in fans moving more air than is required to exhaust or supply the space being served. Minimizing this cost can be accomplished by minimizing the pressure differential between the exhaust and outdoor air paths. This can be achieved by fan placement. A blow-through supply and a draw-through exhaust will have by far the largest pressure differential and the largest leakage. Draw-through is the most common arrangement, while blow-through could also be used with similar or even better results. This cross-leakage of air has multiple paths. The primary source is from cross-leakage at the wheel face, where differential pressure drives the air from the higher pressure side to the lower. Because the exchanger rotates from one side to another, a seal is required to help minimize this leakage, but allows for the wheel to rotate freely. This is accomplished by either a non-contact seal or contact seal. A common non-contact seal used is a rubber block that is adjusted as close to the wheel's face as possible without making contact. A common contact seal used is a nylon brush that makes contact with the wheel surface. Another source of cross-leakage is carryover. Air will carry over in the media from the outdoor air side to the exhaust. And some exhaust air will carry over from the exhaust to the outdoor air side. This will occur even against a positive pressure differential. Another item that adds to energy cost of the wheel is using a purge sector as shown. This can be used to minimize carryover of exhaust to supply, but at great cost in terms of fan energy. As applied, most energy wheels transfer less than 5% of the exhaust air to the supply. For most commercial applications designed to ASHRAE Standard 62, this is acceptable. Adding the purge may reduce this value below 1%, but the leakage of outdoor air to the exhaust will greatly increase. The leakage characteristics are defined by two metrics, OACF and EATR. OACF, outside air correction factor, is the most telling in terms of added energy usage. This tells us how much extra outdoor air is being taken in order to achieve the ventilation requirement. For instance, a wheel with an OACF of 1.10 means that if 10,000 CFM is needed, 11,000 CFM of air needs to be taken in. 10,000 CFM air is supplied, the exhaust fan sees an extra 1,000 CFM air, adding to the fan energy. And if it's a blow-through supply fan, this would also see the extra air. The following chart shows numbers for OACF. Each line representing a wheel listed in AHRI Public Certification Directory. It shows the large range of leakage one could see with a wheel depending on the manufacturer. The lower range of leakage are wheels that use brush seals. The wheels that tend to leak the most use no-contact rubber seals. For example, at 3-inch differential pressure between the supply and return air side of the wheel, one of these wheels has an OACF of 1.48. For 10,000 CFM ventilation, one would have to take in 14,800 CFM of outdoor air. The best practice is to minimize the static pressure between the exhaust and outdoor air path and utilize seals that minimize the cross flow of air. In this case, a draw-through application with 1-inch differential, the OACF could be as low as 1.05 to 1.07, 5 to 7% cross flow. EATR is not shown on the chart and does not vary as much from wheel to wheel. At 1-inch differential, it will be in the 1 to 3% range. It's important to specify these values as fans need to be properly sized, and this needs to be accounted for in the energy savings. Even though some wheels may leak 48% of the air, more times than not, these values are not shown on schedules or even in some selection software.
Total energy recovery wheels transfer both sensible and latent heat, but airstreams must be adjacent and leakage must be managed. Ventilation load reduction can range from about 60 to 80% in both moist and dry climates, so wheels can usually comply with the minimum requirements of both standard 90.1 and 189.1. They are susceptible to leakage, so they usually aren't used with toxic exhaust. Leakage can be reduced significantly with proper fan placement. Overall, total energy wheels might be the best energy recovery approach for a lot of applications. They offer the best ventilation load reduction performance, but they might not always be the most cost-effective solution for a given application. That's for designers to figure out. Ronnie's following analysis can be very useful.
How much each technology will reduce the ventilation load and save energy depends greatly not just on the technology used, but where it is used. If used in areas where it will be hot and humid during cooling, Region A moist areas shown in the map earlier, devices with latent recovery will reduce the ventilation load the most. Energy wheels will reduce the load in the 70% range, while fixed plate heat exchangers only reduce the sensible load and will reduce the ventilation load in the 30% range. Heat pipes and coil loops will reduce the ventilation load less than 20% on design. This assumes close to equal exhaust and ventilation airflows. If this ratio drops, for instance 80%, so will these values. If in a heating-only region, or in regions where sensible cooling is a concern, as in arid Region B parts of the country, plates and wheel exchangers will be similar in the amounts of cooling saved, 65 to 75% reduction of ventilation load. Coil loops and heat pipes will reduce the load 40 to 50%. Each technology, as discussed, has a cost to recover energy. There is an increase in fan energy from both pressure loss across the energy recovery exchanger and from the added flow at the fans from the cross leakage. For some technologies, there is the added component energy from motors and pumps. If one takes the energy recovered by the exchanger divided by the energy input to obtain this recovery, it will result in a ratio. This ratio is defined as the recovery efficiency ratio. In cooling, this RER is represented as BTU per hour per watt, similar to EER in cooling equipment. In heating, this is represented as watt per watt, similar to COP in heating equipment. With these values, we can see how much more efficient the energy recovery system is at cooling versus the chiller or DX system, and how much more efficient it is during heating than the boiler or gas furnace or electric heat. Obtaining data for a 10,000 CFM system and making this RER calculation for different sized equipment for various manufacturers, these efficiencies can be plotted. The vertical axis represents the calculated RER versus the air handler face velocity shown in the horizontal axis. There's a lot of data behind these graphs. Each window represents the range of spacing and depths for each technology. For instance, the closest spacing a wheel or plate will result in the most energy recovered, but also the most energy required. These RERs define the lower range of the windows. Wider spacing and less depth often resulted in less recovered energy, but less energy required, and define the upper portion of the windows. The exception to this was coil loops, where the mid-range depth and spacing had the best RER. This slide represents use in a hot and humid environment. The first thing one can conclude from this is how much more efficient it will be to recover a portion of the cooling from these devices. An energy wheel in a draw-through application that minimizes leakage will have an RER between 50 and 80. This means that 70% of the ventilation load will be conditioned approximately 4 to 6 times more efficient than if the conventional cooling equipment was used. The fixed plate exchanger may only recover half as much energy in a humid cooling application as a wheel, but this doesn't necessarily reflect on how efficient it does this cooling. It may be as efficient as the wheel, in many cases with an RER of 30 to 60. Heat pipe and coil loops will have an RER of 20 to 40 at the 95-degree Fahrenheit outdoor air condition and at typical air handler face velocities. The membrane exchanger will have latent recovery but has a similar RER as the coil loop and heat pipe and is applied at 1/2 the face velocity as the other technologies. What about a hot and dry climate? Here, a fixed plate heat exchanger will be the most efficient. 60 to 70% of the ventilation load will be cooled at an RER as high as 80. The hotter it is outside, 105 degrees Fahrenheit in this case, the higher this number goes. This is opposite of traditional cooling equipment. So the hotter it is, not only is more recovered, it is accomplished more efficiently. Not to say at part load this equipment won't be efficient. If the energy recovery equipment has an RER of 80 at 105 degrees Fahrenheit, at 85 degrees Fahrenheit, 1/3 of temperature difference, the RER would still be 27. Energy wheels, even though they may have 5% or more higher effectiveness, they will have a higher pressure drop and require more fan and input energy to run, so are less efficient at recovering this energy at sensible cooling environments. Heat pipes and coil loops may be less than a wheel, but will still be more efficient by a factor of 3 or more than new cooling. At winter heating, the chart looks similar to the sensible cooling chart. This chart, however, is represented in watt per watt in the same terms of COP. Considering that one's gas furnace or boiler is at best still going to be less than 1 COP, using energy recovery will get an RER of 30 to 80, thus 30 to 80 times more efficient. One thing not represented in this chart is the effects of humidification. If a space is humidified, an energy wheel will help reduce this humidification load in addition to the heating load. Another concern, if a space is humidified, it increases the likelihood of frost on the exchangers. An energy wheel will be less likely to have frosting issues. We have compared technologies on how much energy one can recover and how efficient this recovery can occur. The next two graphics make an attempt to compare installed cost add to recover this energy. One can just consider the exchangers themselves, but the added footprint, casing, spacing, access, fan motor horsepower, filtration, pumps, etc. need to be considered. This graph represents a heating or sensible cooling only application, like a dry climate. Considering all these things, the installed cost add per BTU recovered is going to be very similar for wheels and plates, with plates slightly higher. Heat pipes are considerably more than a water coil, but when the installed cost of adding a pump package is included, it brings the coil loops and heat pipes close together, but much more per BTU to add than plates or wheels. However, when looked at in humid cooling climate, the benefit of the energy wheel doubles. Thus, installed cost per BTU is cut in half. One item that may not be apparent in the graph is that the cost per BTU per hour for coil loops will keep going down the more air the system has, while wheel and plates, the cost per BTU per hour will actually start to increase above 25 to 30,000 CFM. This is because they start to get too big to ship in one piece, or often require multiple smaller exchangers. In conclusion, it is clear there is a place for each technology, and not one that will win out each time. The first question to ask when picking a technology will not be what is most efficient, but is cross-leakage a concern? If no cross-contamination is required, this will put one toward a coil loop. If cross-leakage is just a concern, as in an animal laboratory or nanatorium, a fixed plate heat exchanger, coil loop, or heat pipe might do. If this is a comfort cooling and heating application, then it comes down to is it an arid or a heating only application, or is it a humid climate with cooling? This would often get one to look at a plate or a wheel. Sometimes it comes down to just footprint. For instance, if there's a lot of floor space but no height, this could push one to a coil loop or heat pipe. So the one thing that can be concluded, there is an exhaust energy recovery option for almost every application, but there is not a technology that is best for every application. John?
Even if you pick the most efficient technology for the application, if it's not controlled properly, you won't maximize the energy savings. When many people talk about exhaust air energy recovery, they show the effects at design conditions, because that's where the most benefit is, when it's hottest or coldest outside. But what about in between? This chart shows the annual outdoor weather conditions for Atlanta, Georgia, looking only at daytime hours. The colors indicate the number of hours these conditions occur throughout the year, with the reds and the pinks corresponding to the highest number of occurrences, then orange, yellow, and green in the middle, and finally the blues representing those that occur only a few times. As you'd expect, Atlanta has a lot of daytime hours when it's warm and humid outside. But it also has a lot of hours when it's mild. That is, when the outdoor air enthalpy is lower than the exhaust air enthalpy. While exhaust air energy recovery will reduce the ventilation load at these conditions up here, unless you control it properly, it can actually transfer unwanted heat and increase your cooling load at these conditions down here. Now to demonstrate, this schematic depicts an example mixed air VAV system, delivering 30,000 CFM of air at 55 degrees. In this case, a wheel is used to exchange energy between 10,000 CFM of outdoor air coming in and 7,000 CFM of exhaust. Now I'm showing a wheel here, but the principle applies to all the devices Ronnie just discussed. At this point in time, it's pretty mild outdoors, and the dry bulb temperature is 55 degrees. Consider what would happen if we let the energy recovery device continue operating at these conditions. The wheel would transfer heat from the warmer exhaust air at 70 degrees to this cooler outdoor air, warming it to about 65 degrees. This preheated outdoor air mixes with the recirculated return air, and the resulting mixed air temperature is 68 degrees. Since this is warmer than the desired discharge set point of 55, the cooling coil must activate to cool the air down 13 degrees to set point. Now in contrast, what if we turn the wheel off? Without the wheel rotating and with air bypassing, no energy is transferred. The 55-degree outdoor air mixes with the recirculated air, and the mixed air temperature is 65 degrees. With the wheel off, the cooling coil would need to cool the air only 10 degrees, from 65 to the 55-degree set point. So at this condition, operating the energy recovery device would actually cause the system to use more cooling energy, 13 degrees of cooling with the wheel on versus 10 degrees of cooling with the wheel off. Now, if this system includes the capability for airside economizer, it would probably be in economizing mode at this condition. In this case, the outdoor air damper would be fully open while the recirculating damper would be closed. So all 30,000 CFM of supply air is coming in from outdoors, and no mechanical cooling is required. While the system is in economizer mode, exhaust air energy recovery offers no benefit. In fact, unless it's turned off, the device actually increases cooling load by transferring unwanted heat from the exhaust air to this entering outdoor airstream. Now, to accommodate economizer operation, add bypass dampers to allow full economizing airflow without significantly increasing the airside pressure drop and fan energy consumption. As Dennis mentioned, this is part of the ASHRAE 90.1 requirement related to exhaust air energy recovery. Now, the approach for turning an energy recovery device off differs among the various technologies. It's pretty straightforward with a wheel. Just turn off the motor to stop the wheel from turning. Similar for a coil loop, you just turn off the circulating pump. But other types of devices can be more challenging. For fixed plate or fixed membrane heat exchangers, you need a way to prevent one of the two airstreams from passing through the heat exchanger. With plates, this is commonly done with face and bypass dampers. Here's the photo that Ronnie showed earlier. Again, the airflows are cross-flow with outdoor air entering back here and passing through this way, and exhaust air entering down here and passing through up this way. Plate exchangers are unique in that they can be constructed with a bypass path through the middle of the heat exchanger. Here's the opening for that bypass path, and here you can see the block off on the outdoor air side. So when these bypass dampers are open and the face dampers are shut, all the exhaust air passes through this opening in the center of the heat exchanger, and no heat is transferred. Now, finishing up with the rest of the technologies, membranes aren't currently constructed with an integral bypass path, so you need a separate path coupled with face and bypass dampers. Heat pipes typically use a bypass path with face and bypass dampers, but some styles may offer one or more solenoid valves that can prevent refrigerant from moving inside the tubes and avoid heat transfer. Let's use the same example system and now look at a cooler outdoor condition, 40 degrees. We're still bringing 10,000 CFM of outdoor air in, but during this cooler weather, the VAV system is delivering only 18,000 CFM, and the discharge air temperature set point has been reset up from 55 to 60 degrees. Again, let's consider what would happen if we let the energy recovery device continue operating at full heat recovery capacity. The wheel would transfer heat from the warmer exhaust to the cold outdoor air, warming it to about 60 degrees. This preheated outdoor air mixes with the recirculated air. The resulting mixed air temperature is 64 degrees. Since this is warmer than the desired discharge set point of 60, the cooling coil must activate to cool the air down 4 degrees. So the wheel just overheated the air, requiring recooling. So what if we turn the wheel off? With no heat transferred, the 40-degree outdoor air mixes with the recirculated air, and the mixed air temperature is 53 degrees. The heating coil must now activate to warm the air up 70 degrees to the desired 60-degree set point. So if we turn the wheel off, we're not taking advantage of its ability to recover heat. Instead, we're using new energy to heat the air. Now, obviously, the right answer is that we want to use the energy recovery device, but we need to have some way to limit its capacity so it doesn't overheat the air. In this example, the exhaust side bypass dampers are modulated to partially open. This reduces the amount of warm exhaust air passing through the wheel. With less warm air passing through this side, the outdoor air passing through this other side does not heat up as much, warming to only 52 degrees compared to 60 degrees when no air was bypassed. The resulting mixed air temperature is now 60 degrees, so neither cooling nor heating coil need to operate. Again, the approach for modulating the capacity of the energy recovery device differs among the technologies. Many coil loops use a three-way valve to reduce the flow rate through the supply side coil when less heat transfer is desired. Alternatively, you could equip the circulating pump with a VFD that could reduce the fluid flow rate and reduce heat transfer. Heat pipes use face and bypass dampers, multiple integral solenoid valves, or in some cases a tilt control mechanism that makes it harder for the condensed liquid to flow back to the other end of the heat pipe. Fixed plate heat exchangers use the same face and bypass damper configuration that I showed earlier, but modulate those dampers to vary capacity. Fixed membrane exchangers would also use face and bypass dampers for this. And while some manufacturers suggest using a VFD on the wheel motor to vary capacity, Trane recommends modulating the exhaust side bypass damper like I just described. Ronnie, I know a lot of people ask about that. Can you elaborate?
Wheel energy recovery capacity can be controlled by either reducing the wheel rotation speed or using a bypass damper to bypass air around the wheel. For systems that are not 100% outdoor air, a bypass damper will be present to enable economizing where it is required. Thus, there is no cost add for additional components to control capacity when using bypass. Using a bypass will also save exhaust fan energy during hours when only partial recovery is required. The primary advantage for using bypass besides cost is controllability. Bypass control will have a near linear response. However, utilizing a VFD on the wheel will not. Shown is the sensible heat recovery capacity plotted from laboratory data for both methods. With speed control, after an 80% reduction in speed, there is only a 10% drop-off in heating performance. The last 10% in speed reduction will result quickly in another 30 to 40% capacity reduction. Most wheels will have a 10-to-1 turn down or 20-to-1 turn down maximum. This capacity will not go to zero, as at the minimum speed point, most wheels will still be turning 2 to 4 RPM. Bypass will not go to zero either, unless the wheel is turned off. Some air will still go through the wheel when bypass is 100% open.
The final subject I want to mention related to control is frost prevention. During very cold weather, as more and more heat is removed from the exhaust air stream and transferred to the outdoor air, the condition of this exhaust air can be cooled to the point where it reaches a saturated condition. The result is that water vapor begins to condense on the exhaust side of the device. If the surface temperature of this device is colder than 32 degrees Fahrenheit, this condensate can freeze, blocking airflow and possibly damaging the device. Now, how often this frosting can occur depends on the outdoor temperature, device effectiveness, and how humid the exhaust air is. During the winter, the air inside most buildings gets pretty dry too, unless there's a humidification system. The drier the indoor air, the less likely frosting will occur. And it also depends on whether a sensible or total energy recovery device is being used. This green line shows the condition of the exhaust air as it passes through a total energy recovery device. The red line depicts sensible recovery device. As the exhaust air passes through the total energy recovery device, the transfer of water vapor from the exhaust air to the drier outdoor air stream keeps the condition of this exhaust air further away from the saturation curve for longer. Sensible recovery devices do not transfer water vapor, so the leaving exhaust air condition reaches saturation and frosts at a warmer outdoor temperature than it would for a total recovery device. Now, depending on the application, some method may be needed to prevent frosting from occurring. Again, the method of frost prevention varies among the technologies, but it either involves reducing the heat recovery capacity or preheating the air before it enters the device. Coil loops typically use the same three-way valve, but this time to keep the fluid temperature warm enough so the surface temperature of the exhaust side coil doesn't drop below freezing. Heat pipes and fixed membrane heat exchangers modulate the face and bypass dampers to reduce heat transfer and prevent frosting, while wheels modulate the supply side bypass damper to accomplish the same thing. Fixed plate heat exchangers are the most susceptible to frosting, so they're a bit unique. Ronnie is going to explain this a bit more.
Because of their cross-flow configuration, fixed plate heat exchangers are most susceptible to frost in the corner of the heat exchanger where the cold entering outdoor air recovers heat from the exhaust air on the leaving edge of the heat exchanger. In this corner, the exhaust air is in contact with the coldest surface of the heat exchanger, which approaches the entering outdoor air temperature. This means that frost will form when the outdoor air temperature drops below 32 degrees Fahrenheit. Where frost is the biggest concern is when the space dew point temperature is above 32 degrees Fahrenheit. This will create the opportunity for liquid condensate to form on a surface that could be below the freezing point. Some add a frost avoidance damper to divert exhaust air away from the cold corner when frost may occur. In this case, a temperature sensor monitors the temperature of the exhaust air leaving this cold corner of the heat exchanger. When the monitored temperature falls below the frost threshold, the frost avoidance damper closes to divert the entering outdoor air away from that corner. This keeps the temperature in the cold corner above freezing, allowing for the heat exchanger to operate at a much lower outdoor air temperature.
So far, the methods of frost prevention we described each involve reducing the heat recovery capacity of the device. So that means you also get less energy savings during the coldest times of the year. As an alternative, any of the technologies could use a preheat coil to warm either the outdoor air or exhaust air before it enters the device. This strategy is most common in very cold climates or for applications where frosting is expected to occur for many hours throughout the year. In these cases, spending a little bit of energy to preheat the air enough to avoid frosting may be warranted because it allows the energy recovery device to continue operating at full heat recovery capacity during the coldest weather. Now, to summarize this discussion on controls, I'll use this chart which depicts the control sequence for a total energy reel when used in a conventional mixed air VAV system. When the enthalpy of the outdoor air is higher than the enthalpy of the exhaust air, turn the wheel on and close both bypass dampers. In this region, the wheel lowers the enthalpy of the outdoor air, saving cooling energy. And down here, when the outdoor enthalpy drops below this exhaust air enthalpy, the wheel is turned off and bypass dampers are opened. In this region, you don't want to transfer unwanted heat and add to the cooling load. Now eventually, when it gets cold enough outside, that the air handler will need to activate heat, the wheel is turned back on. Think of it as the first stage of heat. The supply side bypass damper is closed, but the exhaust side bypass damper may modulate if necessary to prevent overheating the air. Finally, at extreme cold conditions, some method of frost prevention may be necessary. Note that this chart depicts the control sequence for one type of device in one type of system. If you want to dig into this stuff deeper, the Trane application manual on air-to-air energy recovery has this type of control mode chart for lots of combinations. Mixed air or dedicated outdoor air systems, constant volume or VAV, air side economizer or not. And it discusses the various methods of capacity control and frost prevention. We covered a lot of information today on this topic. So to summarize, Dennis described how the 2010 version of ASHRAE Standard 90.1 and Standard 189.1 both require the use of exhaust air energy recovery in more and smaller systems. The expected increase in the use of this technology to meet codes is one of the reasons we decided to produce a broadcast on this topic. Total energy recovery devices transfer not only sensible heat, but also water vapor. For climates with humid weather, this results in greater cooling energy savings and larger plant reductions than sensible recovery devices alone. In addition, since total energy recovery devices are less susceptible to frosting, they can often result in greater heating energy savings too. But as Ronnie discussed, there are multiple technologies, each with their own advantages and drawbacks. So the right choice often depends on the project. Next, to maximize energy recovery and minimize the size and cost of the heat exchanger needed to meet codes, design the system to bring back as much exhaust air as economically possible. Ronnie, talk us through how you and your team have addressed this by bringing back toilet exhaust also.
One way to maximize energy recovery is to get all available exhaust air to the recovery device. This may include multiple classes of air. Many systems have two sources of exhaust air: return air from the spaces, which is exhausted to maintain building pressure, and some recirculated back to the space. The other source is toilet exhaust from restrooms, where required by code. This air is not recirculated. One way to accomplish this is depicted in the slide. Toilet exhaust is isolated from return air on the inlet side of the wheel. Exhaust air enters the first portion of the wheel. System exhaust from the return air enters the second portion of the wheel, purging toilet exhaust air from the wheel and minimizing any carryover. Here is how the exhaust portion of the system works. The exhaust fan speed modulates to control building pressure. The toilet exhaust damper modulates to maintain code-required exhaust airflow from the restrooms. This exhaust airflow is measured. If the toilet exhaust air damper goes 100% open, the balancing damper will modulate toward close. Though unlikely, this system can bring the minimum building exhaust flow down to 100% toilet exhaust flow, if required, to maintain building pressure. So the system can ensure building pressure control, proper toilet exhaust, and be able to get the maximum energy recovery possible.
Sometimes we get questions about using exhaust from restrooms in a wheel application. ASHRAE Standard 62.1 addresses this in its requirements for recirculation or transfer of air within a building. The standard allows toilet exhaust, which is defined as Class 2 air, to be used for energy recovery as long as the transfer, carryover, or leakage of this Class 2 air is no more than 10% of the resulting outdoor air intake flow. If you're using an AHRI certified wheel, this cross-leakage measurement is part of the certified performance, so it's readily available. ASHRAE Standard 84 and AHRI 1060 both define the term exhaust air transfer ratio. This is the percentage of the airflow leaving the supply side of the device. That's location X2 in this diagram, which is made up of air that leaks or transfers from the exhaust side of the device, location X3. So as long as the EATR is 10% or less, ASHRAE 62.1 allows the use of toilet exhaust for energy recovery. Of course, if only a portion of the exhaust air is from restrooms, then the EATR can actually be even higher. With that said, with proper fan placement, the EATR for most wheels is well below 10% for most applications, so it's usually not an issue. Next, we spent a good deal of time explaining why proper control is important to maximizing the energy-saving benefit of the device over the course of the year. Turn the device off during mild weather to avoid wasting energy, and modulate its capacity during cold weather to avoid overheating. And in many climates, an airside economizer can provide the benefits of free cooling for much of the year. In a mixed air system, bypass dampers should be included to avoid higher pressure drop when outdoor airflow is increased for economizing. And in cold climates, you may need to provide some means of frost prevention. The last suggestion is to specify and purchase energy recovery equipment that has been certified with AHRI. Most manufacturers participate in the certification program, which allows you to specify energy recovery components with greater confidence and ensures an apples-to-apples comparison of performance.
Well, we hope you learned a lot about air-to-air energy recovery today. There are a number of publications available that provide more information on the material we covered, including the application manual that John mentioned. A bibliography detailing these resources is included in your handout. Additionally, past broadcasts are available on DVD at trane.com/ENL, and many are available on demand free of charge. Visit trane.com/continuing education for a complete list of on-demand courses available to satisfy credentialing requirements. Many of these are lead specific. Remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your member information to your local site coordinator. Finally, we're excited to announce our 2013 Engineers Newsletter Live program lineup. We'll start the year with a discussion on single-zone VAV, and in spring we'll discuss ASHRAE Standard 62.1. Then we'll return in fall to discuss variable speed chiller plant operation. So contact your local Trane office for details. Thanks for joining us today. We'll see you next year.